Let's work out the next problem here. Problem 15. We have a 15 kilogram block, as shown. So let's assume coefficient is 0.4. Will we actually get the block moving? So let's get the maximum static friction. That's going to be mu static times the normal. And I'm not going to put anything into a formula until I've drawn a free body diagram. So I have a normal, I have a weight, I have F1, and I have a friction force. Now I know that the normal and the weight balance, so I can say that the normal equals 15 times 9.8, only because I know these two forces balance. So when I actually take 15 times 9.8, I end up getting a normal force of 147 newtons. And so let's get that friction force of 0.4 times 147, and that's going to end up giving me 8. And you know what? I'll have to calculate that now, and I get 58.8 newtons. Now, that's what I need to get it moving, but I'm only applying 20. So the answer is no, it won't. Now, for part B, let's add, so we want to know how much will it take to get this thing moving, so let's calculate. Based on the free body diagram, we got normal, we got F1, we got F2, we got the weight, and we've got this friction force. I know that the max static friction is 58.8. I know that F1 is 20. So what do I need F2 to be to overcome friction? Well, I need F1 plus F2 to balance the friction. So that's going to be 20 plus F2 equals 58.8, and so I get F2 is going to be 38.8 newtons. Finally, we get the block moving, and now we only need 10 newtons to keep it moving. So now we're talking about kinetic friction, moving friction. So let's actually solve for this coefficient. So I've got the normal, I've got the weight, I've got F1, I've got F2, and I've got my static and my kinetic friction here. So once again, from this calculation up here, I know that my normal force is 147 newtons, and so I know that F1 plus F2 still equals my friction. So let's get the friction force, which is 10 plus 20, and that's 30. So now friction is fun. That's the formula we use. So we're going to end up getting 30 equals mu times 147. And so I'm going to get mu. I'm going to round this a lot. Mu is going to be, I think, you know what, it's going to be about 0.2 when I calculate it out. A little bit bigger than 0.2. And then finally, when we cut F2, what's going to happen to the box? So let's write this out. I'll use this nice little font here. What happens is that the box will slow down to rest because there is not enough force to overcome friction and keep it moving. And the way we show that also with the free body diagram is we would draw it like this. So hopefully I can scroll down a little bit more. Good. So I'll have the normal, I'll have the weight, I'll have F1, and I'll have this big friction force which overpowers it and slows it down.